Okay, so first things first, you need to know that we're talking about logarithms because, hold on a second. Okay, we're talking about logarithms today, and the reason is, technically a logarithm is just the inverse function of the exponential graphs, okay? So the inverse of an exponential function is a logarithmic function, okay? Logarithmic. Okay, so let's talk about this for a minute. It's really important you understand that the log symbol, as confusing as some people think it is really just invented out of necessity. Let me show you why. Let's say I gave you f of x was 2x, right? And I said, let's find the inverse. How do you do that? So remember, this means y equals 2x. So how do you find the inverse? You switch x and y around, right? Okay, so you go x equals 2y. And then what you do is try to isolate the y. So you would get y equals 1/2 x. And you could conclude that if f of x is 2x, then f inverse of x is basically half x. Right? That's pretty easy. But if the function is 2 to the x, we've got some issues. So let's go back and revisit this problem now. Let's say it's not 2x, but 2 to the power x. What are we going to do with this thing? Well, this is something the mathematicians wondered too. So what they did was they wrote this as y equals 2 to the x. They switched the x and y around, right? X equals 2 to the y. Then they say, okay, it's time to solve for y. How? How do you get the y by itself? See the problem? Can't divide by 2. That's not going to help. Multiplying by y doesn't do anything. I guess you could take the y-th root of both sides. The y-th root of x equals 2. I isolated 2. I was trying to isolate y. See the problem? Mathematicians had the same problem. How do you get the y by itself? I don't know. So one guy said, I'll do it. Check this out. And he wrote, there. Y equals log base 2 of x. And some other guy came over and looked at his paper and said, why'd you write log little 2? He goes, I don't know. I just made it up. And that's exactly where it came from. Okay? I mean, it wasn't two guys in a coffee shop or something. It was mathematicians needing a new symbol to accomplish this task. They just needed the y by itself. And so the log was invented. And I have no idea why it's log. I'm not a history guy, so all I know is it's log base 2. But really, it's just the inverse of 2 to the x. Okay? So now you kind of know roughly where it came from. Kind of. All right. So now that we know that that's sort of the necessity there, I need to erase this stuff here. Let's go ahead and write down some of the terminology and some of the things that we know about logarithms. Because after something like this is invented, it all becomes very, very interesting. It's kind of like I, you know. I was like, who wants to talk about imaginary stuff? But then once it was invented, it was like, wow, this is really profound stuff. Logs are sort of profound. Not as cool as I. But anyway, the logarithmic function of base A, where A is a positive number and not 1, is denoted by log little a and then an x. And this is pronounced y is the logarithm to the base A of x. I will just say log base A of x. Okay? Okay, the domain of a logarithm function is going to be the range of yesterday's function. Okay? Because we know that whenever you do an inverse, right, domain and range trade roles. So that means that yesterday's range will go in this blank. Why don't you guys go back and look in your 4.2 notes real quick. Look for the range of y equals a to the x, because that's going to be the domain of log base a of x. Okay? They're inverse functions. So go back in your notes, look back. What was the range yesterday? Because that's the domain today. Find it? So what is it? Blake? Yeah, yesterday the range was y is greater than 0. Today the domain is x is greater than 0. Correct. Okay, so what this means is whenever you're dealing with an expression like this one, this number can be anything. But this number here, this little a, has to be positive but not 1. And this x must be greater than 0. Okay? So the y here is anything, 1, 0, negative 1 pi, whatever, e. The base here has to obey the same rules as the base yesterday. And I said we would not talk about negative bases, it's silly. 0 is silly, 1 silly. But numbers like a half or a third or a tenth or 1.4 or 10 or 1,000, those are meaningful. So numbers that are positive but not 1. And then the domain of the log, that means whatever is after the log base a must be positive only. Okay? And that's, written as x is greater than 0 here. Okay? Okay, let's go and look at this next section. Can I erase the ink? Yeah. Okay. So, first of all, let's just practice rewriting some of these. Because all of these that have logs in them can be written without logs, and all that don't have logs can be written with logs. So I'll do the first one and the third one, and you guys will do two, B, D, and E. Okay? So the first one, I can rewrite this as 3 to the 5th equals 243. 3 to the 5th equals 243. Why? Because, how did I say we pronounce this thing again right here? Log what? Base 3, correct. So I know that the 3 is the base. See that? This is a log base 3, and I'm trying to write an exponential base 3. So I need that 3 there. Okay? Also, remember the logarithm was invented with the purpose of isolating the power. Okay, that was the whole point. Try to get the power alone. What's alone in this problem? 5. The 5 is alone. Therefore, it must be the power. See? As for the 243, that just goes on the other side of the equal sign. See if you can rewrite b in exponential form as well. So you do part b now. Okay, so it's the negative 2 that's alone. That means it must be the power in the original exponential function. And the base here is clearly 5. It's right there in the small font under the G. So it's going to be 5 to the minus 2. And this is equal to the 125th. Obviously, this is a true statement too, right? 5 to the minus 2 really is 125th. And 3 to the 5th really is 243. So you want to make sure your final statement makes sense. You don't want to write something silly like negative 2 to the 5th is 125th. That's not even true. Okay? How about this one? Now this one is in exponential form and it needs to be written in log form. So remember the mathematician's desire was to isolate the power. So that means the 4 is going to be all on its lonesome self. Okay? All by its lonesome self. 4 is alone. And the base is 2.5 clearly. So that means there's a log base 2.5 here. Yes, you can have a decimal base. The rule was you cannot have 1, 0, or a negative. But you can have a decimal base. And that got all messed up. Let me scroll back down. The m just kind of stays right here. Okay? It is now the input. See? In this statement here, 2.5 to the 4th, m is sort of the output. But right now, it's the input of the log. See that? It's what's being plugged into the log function. Okay, and this one, e to the b squared is 7. Try that one. See if you can get the b squared by itself. And then see if you can get the 2 by itself. Using a double log. Just for fun. The 2. If you do 2 iterations of log, you can get the 2 all by its lonesome self. Okay, so your first iteration of log, you're going to be able to isolate that b squared, and you're going to have log base e 7. If you want to get the 2 by itself now, then you would log it again. This time you, of course, use a base b. So you could technically write it like this. 2 equals log base b of log base e of 7. Like that. You got the 2 all by itself. Or we could have isolated b by square rooting, or whatever we want. But I just thought it was kind of fun to isolate the 2 there. Yes?
Wait, is it when you multiply two logs, can you add the bases?
No, we will talk about what to do with multiple logs later. This is not one of them. These are 2 composed logarithms, one inside the other. We don't have any rules for that necessarily. So I will say this, though. If you ever see a log with a base e, that can be abbreviated as ln. You might remember that. So how many of you remember that this is actually written ln?
Natural log.
Natural log, yeah. Well, anyway, for now we can leave it as log base e, but later in the lesson I'll be changing that to ln. It actually is because the French got to it first, and they say log natural base. We say log with natural base. They say we say natural log, which means base e. They say log natural, so it's like reversed grammar. But anyway, the French did a lot of the work with the logs, and so they got their name on that. So we just let them use ln. Not that we can do anything about it. So, okay, a to the third is 31. How would you write that one? What would that look like, class? The 3 would be alone, right? Log base a, 31. Yeah. And people teach this a variety of different ways. There's so many ways to teach this, but I think it's best for you if you understand that the goal was to isolate the power, and so the power should end up on its own. Okay, that's kind of why it was invented, and so let's stick to that method if we can. All right, let's go on. Finding the value of a logarithmic expression. So how do you find the values of these? I'm going to actually give you the first 2 answers, and let's just see if you can figure out what this all means, okay? So the answer to this first question is simply 5, okay? That's it. I just did it in my head, okay? It's because I know what a log means. And the next one is actually -4. So just with your neighbor, see if you can figure out how I came up with that so quickly and why that is the correct, those are the correct answers. Okay, take a moment and do that. Okay, so the first question, it's really just asking what power of 2 produces 32? 2 times itself how many times makes 32? 2 to what power makes 32? That is the question. So it's the 5th power. If you want to, you can write the question like this. 2 to what power makes 32? And then you can simply rewrite the 32 as 2 to the 5th. Like this. That way you don't have to do any guessing. Just cross out your 2's, like you did last night. Okay? Or tonight if you haven't done the assignment yet. The next one can be understood to mean 3 to what power makes 1 over 81? But 1 over 81 is the same thing as 1 over 3 to the 4th. In other words, 3 to what power equals 3 to the -4? -4. That's the answer. Cross these out. Okay, so you can do them in your head, or you can write them in exponential form and then solve them. Either way. Okay? Let's talk about that third one, though, because that's not one that you could probably do in your head, even if you know what a log means. So what you want to do on this one is literally write down something like 27 to what power makes 81? So go and write that, because that's what it means. The answer is not going to jump out at us right away, but if we rewrite the 27 as 3 cubed, and we rewrite the 81 as 3 to the 4th, we can cross out the 3's, and we end up with the situation 3x equals 4. So I know, Jack, you had your TI-89 solve this one already, right?
Yeah.
Did it say 1.33333? Yeah, 4/3. 4/3 is the answer. So Don't you wish you had a TI-89? But Jack, make sure you know how to solve it by hand, because on the test, obviously, I wouldn't let you use that. So 4/3. Okay, I want to say something real quick about this before we leave the page. Did you notice that when I have a number larger than 1 as my input, the logarithm popped out positive? Don't miss this. But when the number here was less than 1, the answer came out negative. Okay? So even if I couldn't do log base 27 of 81 in my head, I know it's a positive answer, because 81 is bigger than 1. And I've got a base bigger than 1. So this just means the answer is going to be positive. So whenever this is positive, the answer is positive. That's what I'm saying. That's for bases that are bigger than 1. Okay? Okay. We'll talk about some of the really exotic problems later, like where the base is like rad2. Like how do you deal with that? Stuff like that, we'll deal with it later. Or sometimes you have 2 different bases in the same problem. That's all to come. All right, let's go on. Okay, so let's just review. We said that the domain of a function's inverse is just the range of the original function. And the range of an original function, or of an inverse, is the domain of the original function. So this is just a true statement in general. Something we've mentioned before in this classroom. Okay? So we could summarize that by saying the domain of a log function is just the range of an exponential function. Right? X is greater than 0. Or you can say 0 to infinity. Also, the range of a log function is going to be the domain of an exponential function, which is all real numbers. Which you can just write as negative infinity, infinity with our interval notation. And those are down here. This is like a little summary box. But we've already said it up above. Okay. So let's take a moment now and do these example 3 problems. Can I erase the ink? Okay. Let's go down here and let's find the domain of these functions. Okay? The first thing we said was that a logarithm has to have a positive domain. Okay? So that was the rule above. Domain is positive real numbers. So what that means for us is that a logarithm will never eat any negative number, and it will not eat 0. So you cannot feed it those numbers. You cannot feed it a negative, and you cannot feed it 0. It doesn't even know what to do with that. Okay? Will not ingest it. Will not digest it. So look at this. This x plus 3 better be a positive number, or the log won't even take it. So how can I make that happen? I can write x plus 3 is greater than 0. I require this. Logs require this. So what does this solve to give us? X is greater than negative 3. Or in interval notation, negative 3 infinity. Okay? Let's look at the next one. This is a much harder one. We require this to be positive. 1 plus x over 1 minus x greater than 0. How in the world do you solve this? A rational inequality? We didn't do that yet. That's in section 3.5. I think it's 3.5 or 3.6. We skipped it. How do you solve that? Let me show you. It's not hard. Don't cross multiply it. This is not an equal sign. Okay? Besides, you're going to lose all this important stuff. Okay, so what I do on these is I just draw a number line. Okay? Just draw a little number line. It's like a little x-axis. Like this. And I put on it the roots of the numerator and denominator. So what number would make the top 0? Negative 1. So that's going on my number line for sure. Now look at the denominator. What makes the denominator 0? 1, right? I put that on my number line. These are two very important numbers, and here's why. If I plug in 0.9 into this, you get positive over positive, and this becomes a true statement. But if I plug in 1.1, just to the other side of 1, the top is positive and the bottom is now negative, see? And if I plug in negative 0.9, then the top is positive and the bottom is positive. But if I plug in negative 1.1, then the top is negative and the bottom is positive. In other words, negative 1 and 1 are crucial values here. They're critical. They're so important. They are the roots of the top and bottom, and they will greatly affect whether this statement comes out true or false. See? So the first thing I did was what? I found the roots of what? Numerator and denominator, and I put them on a what? A number line, right. This makes the problem really easy now. All I need to do is test a number from the left, the middle, and the right. We've done this sort of thing before, okay? So let's go ahead and pick a number that is over here. So let's test x equals negative 2. And we'll just plug it into this 1 plus x over 1 minus x is greater than 0 statement. Let me rewrite that, I just erased it. 1 plus x, 1 minus x greater than 0. Let's plug in negative 2 and see if it comes out true. Okay, so you plug in negative 2, and you get negative 1 over 3 is greater than 0. Negative 1/3 positive. No, not true. Okay, so do not shade. That was false. Okay, so this is false. Let's pick a number between negative 1 and 0. What would we maybe want to pick between negative 1 and 1? Yeah, you want to test 0 in here, right? So let's test x equals 0. If you plug in x equals 0, you're going to get 1 over 1 is greater than 0. That's true. Okay, so we'll shade the middle. Okay? And so that's going to look like this. And then maybe we could test like x equals 2 out here, you know. But it's going to come out false because it's going to give us 3 over negative 1 is greater than 0. That's not true. Okay, so I demystified a hard problem by using a number line. It's a great little organizer. Okay? So what's my answer? What's my domain? Greater than negative 1 and simultaneously less than 1, right? So just put this, x is between negative 1 and 1. There's your domain. So that was a tough one, but I tried to use that number line to simplify your thoughts. Okay, the next one is actually a pretty easy one. I'm looking at this, and the rule is this must be positive or the log won't eat it. So absolute value x must be positive. Isn't that kind of always the case anyway? I mean, whatever I plug in here for x, right, the log is going to eat it because the absolute value will take care of any negatives. The log will say, thank you very much, and eat it. There's one exception. There's one number that I cannot make positive using an absolute value. 0. 0 itself. If I plug in 0, the log will say no thank you. But if I plug in negative 50, the log will say yes, thank you, because of that absolute value. So this is all real numbers except 0. Okay? So basically you can just write x is all reals but not 0. We've done that before, right? So I'd like to show you the graphs for these two things right now real quick. I'm not going to use my graphing calculator because I don't want to teach you how to type in the base 5 and the base 2 and base half and all that. So I'm just going to show you. This is really just a log graph shifted to the left 3 spaces. So the first one, the graph kind of looks like this. And the domain is from negative 3 off to infinity. Okay? The second graph, basically if you plug in numbers, or if you use a graphing calculator, you'll see it looks kind of like give me one second. Something like this, I think. And it's sort of stuck between negative 1 and 1. It sort of lives in that little region, and there's nothing outside that region, just like the domain says. And the last one looks like this. And it lives everywhere except at 0. There's a little gap in the middle. Okay? So you could have cheated on these and graphed them all and looked at them and said, oh, the domain is greater than -3. Oh, the domain is between -1. Oh, the domain is empty with 0. But that is really cheating, isn't it? So look at the graph and declare the domain. We want to be able to do it by hand. And then verify it with a graph. Okay. All right, let's summarize again. What did we say the domain of a log is? What will they eat? Positives only, right. Okay. Positive real numbers only. What is the range? It's our domain from yesterday. All real numbers. Okay, let's draw a log graph. Okay? So yesterday you wrote down this graph. You drew this one. This is y equals 2 to the x. And I asked you to memorize it, and if you look on the whiteboard over under Honors Pre-Calculus, you'll see that I need you to make a flashcard for this graph, and 3 to the x, and e to the x, and you can put them all on one flashcard if you like. Kind of nice to do that. Okay? So that's for Friday. Question? Yes. Okay. So this is yesterday's graph. Today we've inverted it. So what's it going to look like? Well, when you invert, you reflect over this line. Always. This is sort of the magic reflection line. So what's it going to look like? Well, it's going to be over here now. I'll draw it in blue. This is y equals log base 2 of x. And it contains the point 1, 0 and 2, 1. Remember, the x's and y's just switch roles. Okay, it's good for you to see this graph because, honestly, you don't want to have to rely on your calculator every 2 minutes and say, oh, what does a log graph look like? You need to understand it's just a reflection of the exponential curve. That's all it is. Okay, remember yesterday's graph had a horizontal asymptote? Had a horizontal asymptote where? Yesterday's graph. Right on the x-axis. Remember that? So there was a horizontal asymptote at y equals 0. But today's graph has been reflected over the y equals x line. So x becomes y becomes x. So y equals 0 is not the asymptote anymore. What is the asymptote now? X equals 0, which is not a horizontal line at all. It's what? A vertical line. So we have a vertical asymptote at x equals 0. See? So this is a brand new graph, this blue one. It has a vertical asymptote at x equals 0, passes through the point 1, 0, and 2, 1. Okay, let's describe it a little bit. As you can see, the x-intercept is clearly 1, 0. There is no y-intercept this time. Yesterday it was the other way around. It is the y-axis that is a vertical asymptote today, whereas yesterday it was the x-axis that was a horizontal asymptote. See? A logarithm function is decreasing if your base is a fraction. 0 is less than a is less than 1. And it is increasing if your base is bigger than 1. So I've drawn for you this blue graph. What's the base? What's the base of the blue graph? 2. Is that bigger than 1 or less than 1? That's bigger than 1, last I checked. Okay? So that's why this graph is on the rise. See that? If you were dealing with a base that's like a fraction, okay? I can draw that for you too real quick. Understand that it came from something like half to the x. So yesterday we drew half to the x, looks like this. See? And when you reflect that thing, it's going to look like this. When you reflect it over this line. So it's going to be decreasing. This is the graph of y equals log base half of x. So this is what bullet 4 is talking about. Bullet 4 is just saying, look, if your base is a number like 2, the graph will be on the rise. But if the base is a number like a half, the graph will be falling like this. That's what this is saying. Okay. And then the last statement, the last two statements are, the graph of f contains the point 1, 0, and a1. Just think steak sauce. You guys heard of a1 steak sauce? Okay. So for example, this graph here, this blue graph, would contain the point 1, 0. All logarithms have it. 1, 0. And 2, 1 because it's base 2. And this graph here is a base half. Right? So it contains the point 1, 0 like all the other logs, and the point half, comma 1. Just think steak sauce. A1 is always on the curve, unless it's been transformed. Okay, if it's been moved, then of course that's not true. Okay, and the graph is continuous and differentiable. So that just means, again, continuous, no breaks at all, can be drawn without lifting your pen. Differentiable means nice and smooth, no sharp turns. Okay? All right, so this is kind of the stuff that's newer. And then the rest of this is just a little bit of notation, and we'll draw a graph here. Okay, so if you see an log and there's no base written here, it means what? It really means log base 10. Okay, so this is called the common log. And if you don't see a little number down here, no base indicated, you can assume it's a base 10. Means log base 10 of x. Okay? On the other hand, if you see an ln, that's the natural log, and this means log base e is what it means. Log base e of x, which you should know. 2.71 is the base, 2.71828. There are a few professors out there who, when they write log, they don't mean log base 10, they mean ln. That's very confusing, but it doesn't happen in high school very often, and it won't happen here. So just know if I write log, I mean base 10. All right, let's try graphing real quick. It's not hard, especially since you guys are good at transformations. First of all, we understand that this means y equals negative log base e of x plus 2. That's what it means. Right? And so our parent function is the log base e graph. So the parent function is y equals log base e graph. And it looks like maybe it's been flipped upside down and shifted, but let's deal with that later. First thing I want to do is plot this graph. I know it contains the points, so the parent function contains 1, 0, because it's a log graph. Okay, so let's plot that. And steak sauce, A1. So in this case, E1, right, E1. So it contains the point E1. So it must look like this. Okay, but there's some transformations, right? Somebody slapped a negative out front. What does that do to the graph? Pretty important. What does it do, Eddie? That's right. Reflects it over the x-axis. So now it looks like this. Right? And then somebody put an x plus 2 in here instead of an x. What does that do to the graph? Pretty important. Shifts it which way? Left 2. So the final answer is actually over here. And I do insist that you draw the asymptote. So that asymptote is actually over here now, after everything got shifted to the left. It used to be on the y-axis, but it's been moved. The red graph is your answer, okay? Pretty important. Transformations, learning transformations has been very helpful to us. Like, we've been able to handle just about any graph without getting the calculator out. Okay? All right. Can I erase the ink on that one? Okay. See, I wouldn't ask you to graph something like ln of x squared plus 5 or something, because we haven't really talked about that. Like, how does that transform the graph? So don't worry about it. All right. Let me clear the ink there. And then the last part of this assignment is really easy. I mean, really, really easy. So all you would do is just kind of rewrite these. So the exponential form of this thing would be 4x minus 7 equals 3 squared. So all I did was I rewrote it without the log. And if you solve that, you just get 4. So easy. This second equation, part B here, in example 2, that can be written as 64 is equal to x squared, which means x is 8. Technically, there's two answers to this. X is plus or minus 8, but x was a base. So I can't use the negative answer. I have to just use x equals 8 only. And this next one, you can just write this as 2x equals ln 5, which means x is 1/2 ln 5. No, having an e on the left is the same thing as having an ln on the right. So that actually gets rid of the e, see? And we'll do the fourth example as a warm-up tomorrow. Okay? So your assignment for this is not due until Friday, and I'm not even posting it yet. You have an assignment for 4-2 that's due tomorrow, right?